Welcome, physics class. This is a help video for static electricity terms and concepts. Chapter 18 and 19 together. It's a little bit out of 20 even. The first question says describe charging by conduction. You can charge an object from another object if they touch. Touch and transfer. If you touch something that's charged, you'll get the same charge that it has. If two things touch each other and they both have negative charge on one and it touches the other, it'll transfer negative charge to the other one. What are they going to do? Repel? Yes, because there's only two rules that explain everything about this force. The only two laws that determine the behavior of everything in chemistry in our physical universe, the matter in the universe, all obeys these two laws. Likes repel, opposites attract. God is amazing. He made everything in the universe out of a positive charged particle and a negative charged particle and a neutral charged particle. Neutrons, protons, and electrons make up everything, virtually, 99.9%. He's an amazing God. Pretty creative for three little tiny spheres. Anyway, these two would repel. If they were allowed to move freely, yes. Wish we could show you this stuff. They would move away from each other. I've got some little tiny balls called pith balls. They're made out of pith, which is in the tree. A little like cork, really lightweight, and get charge on them, and they really exhibit this force very well. But other things, you've seen it before. You've seen static charges before. But by induction, if you charge by induction, you just get close. And that forces the opposite charge away. If you've ever rubbed your balloon on your hair, I used to tease my kids with that, and then I could stick it to the wall. Well, how would it make the wall charged? I didn't rub the wall on my hair. But if you get a balloon with negative charge close to a wall, you could draw a wall there. Make up my mind. As you get an approach, it would make the negative charges in the wall move away from that area, and that would leave positive charge behind. Then it would be some attraction. So yeah, it forces the opposite charge away, and it attracts the like charge. I'm sorry, I'm doing that wrong. Forces the opposite charge toward, not away. And it repels the like charge. I've been doing grades all day. I'm so tired. Repels like charge. Yeah, opposites attract, likes repel. So yeah, it's easier to see in the diagram, or actually to see it performed. But you could see there would be attraction. Overall, there would be attraction. Opposite charge comes toward, like charge goes away. Question number 2. Give Coulomb's law. If you've read about it, it's amazing how much like the gravitational law it is. That the force that we sometimes call the electrical force is equal to some constant that makes it a proportionality into an equality. They call it a proportionality constant, K. It depends on the medium, like if it's air or water or whatever the material is. a Bose-Einsteinian condensate, for example. They do experiments with that stuff. But the important part is that it is equal to the charge of one, Q1, Q2, the charge of the other, divided by the distance between them squared. Q1, Q2 over R squared. If you want to make that comparison, gravity was big G, M1, M2 over distance squared. You see the comparison. God is a God of order and symmetry and predictability. He has allowed us this ability to reason so that we may look at what he has made and understand what he is like. All right, number 3. I don't have to wait for you to get that because you can pause the video. What property does the electromagnetic force depend on? Well, the property is called charge. But of course, it's just a name we give this property. When we're talking about gravity, we call it mass. What is mass? Well, I don't know. It's a property that things have, and they exert gravitational force. What is charge? Well, I don't know. It's a property that something has that makes it exert this force, the electrical force. Number 4, how does the electromagnetic force, excuse me, how does it compare to gravity in strength? Oh, many, many times. If you look at this, G is 6.67 times 10 to the negative 11th. Newton meter squared per kilogram squared, there's your mass. Well, the electromagnetic, electrostatics, electrical constant, whatever you want, Coulomb's constant, it is sometimes called, is 9 times 10 to the 9th Newton meter squared per Coulomb squared. You see how much bigger that is than that? 9 negative 11th. So you could say much, much bigger, billions of times bigger. Yes, 10 to the 9th would be 10 to the 18th. So a billion billions. It's even more than a billion times stronger. That's the perfect design that God has made things. Masses are controlled by very huge masses, the planetary movements and things. But little tiny particles that make up atoms need to be controlled by a stronger force. And they are. Much, much stronger. How does, what's the unit label for charge? Well, we know kilograms as the unit label for mass, but we named it after Charles Coulomb, French physicist, and we used that as our unit label for electrical charge. Number 6. How much force would result from 1 Coulomb of charge separated by 1 meter from another Coulomb of charge in air? Well, the equation for electrical force is K, Q1 times Q2 divided by R squared. Well, if that's 1, and that's 1, and that's 1 squared, those are all 1s. So the answer is K, which is just given. In air, Coulomb's constant is 9 times 10 to the 9th Newton meter squared per Coulomb squared. So the answer would be, oh, you don't want all that label in there, because meter squared and Coulomb squared would cancel. Meter squared, Coulomb squared. Oh, so yeah, the answer would be in units of force, which would be newtons. Can you imagine how strong that is? If you had a coulomb of charge and somebody else had a coulomb of the opposite charge, excess charge. We all have charges in all of our atoms and stuff, but I mean excess. 1 coulomb, another person had another coulomb of charge. 9 billion newtons. Oh, gosh, a newton's 4.45 newtons is a pound, so you could divide by 4, roughly. What is that? We're talking about, whoops, 9 billion divided by 4.45, 2, something like that. Yeah, roughly 2 billion pounds. A billion tons. Well, no, it'd be divided by 2,000. Be a million tons anyway. That's a pretty strong force. You wouldn't be able to keep them apart. Like the force of attraction between my wife and I. I know she's within earshot, so I was trying to pay her a compliment. Number 7. If 2 charges become farther apart by a factor of 2, what if that number doubled? Yeah, I know some of you already know this, right? Because we keep running across this relationship. It's like God has built this into a lot of things. Sound, and light, and gravity, and electricity. Double that number, 1/4. You see that? 1 over 2 squared would be 1/4 as much charge, as much force. Number 8, smallest quantity of charge possible as determined by the Millikan in the famous oil drop experiment. We talked about that in 8A section review in the first part of 18, rather, not, I forget which class I'm talking to. Biology is on chapter 8. You guys are on chapter 18. In 18A section review, talked about the Millikan oil drop experiment, and it turned out the smallest amount of charge that we know of in the universe is the charge on the electron. So 1 electron, which has negative, that just means the flavor of, it doesn't mean less than 0. Negative charge is a flavor. It has a different connotation than in mathematics. It tells you something about the nature of the charge, not the magnitude of the charge. It's not, the magnitude is 1.6 times 10 to the negative 19th. The unit label, coulombs. So the electron has a tiny, tiny amount of charge. But how much mass does the electron have? Something like 9.1 times 10 to the negative 31st kilograms. So, and we already know that gravity is so much weaker and the electron has almost no mass. That's 31 zeros after the decimal point. The electron doesn't depend on its mass to hold it to the proton. It depends on its charge to create that force of attraction. That's what holds atoms together. It's what holds the world together. It's what makes life possible. And if the charge on the electron was any other value, the universe wouldn't even exist. And that's not the only number that has to be exactly what it is. Again, somebody going to tell me that's an accident? That this just happens to be so finely tuned that all these little masses and charges and constants, if Coulomb's constant, 9 times 10 to the 9th Newton meter squared per kilogram, Coulomb squared, was any different, we wouldn't be here. So number 9, define the electric field. An electric field is an area that exerts force on charge. Like a gravity field would be An area that you feel force exerted on mass. If you feel force exerted on your mass, you're in a gravity field. If you feel force exerted on charge, you're in an electric field. That Van de Graaff generator we played with in Chem 1, yeah, it generates an electric field around it because it has charge. It can exert force on charge. So an area that exerts force on charge, whatever it is in that area must be charged to be able to exert force on a charge. So yeah, we call them fields because they exert force. There is such a thing as a force field. Most science fiction is derived from real science. Give the equation for the electric field. Well, if electric field is symbolized by E, it's the electric field intensity. Can you describe how much force is exerted on a charge? It would be the force exerted per unit charge, Q. F over Q. And the unit label for that then would be the newtons per coulomb. How many newtons per coulomb of charge is exerted? An electron has an electric field. It exerts force on charge. The proton exerts force on the electron. It has an electric field then. Those electric fields interact. Number 11. So what's more abstract than writing an equation to describe something that's invisible? Well, we do it for gravity, which, by the way, there's just to make the analogy, gravity is how much force there is per mass. Newtons on our Earth, our gravity field intensity is 9.8. We always use the unit label meters per second squared. You could say it's newtons per kilogram. That's the gravity field intensity of the Earth. Well, now we're talking about electric field intensity. Newtons per coulomb. Well, what if you had a positively charged plate like Millikan did? Bunch of positive charge on this plate. And negative charge on the plate below it. This is what he kind of slowed down the electron. There was a little drop of oil, rather, that dripped through here, and the drop of oil was kind of suspended because he turned up the voltage on these plates. It was repelled by the bottom plate and attracted to the top plate. And that's how he figured out how much charge it had, was by knowing the weight of the oil droplet and the electric force exerted by these two plates. Well, we can draw lines to represent this force. So just by convention, we've all agreed that what if we put a little positive charge between those plates, draw a line that would represent the direction that it would exert force on that positive charge. If I had a little positive charge right there, which way would it go? It would go down. And if I had it there, it would go down. And anywhere in between here, that positive charge would be pushed down to the negative charged bottom plate. Yes. And you notice that they're all parallel lines except at the very end. If you had a positive charge, for example, sticking out here, which way would it go? It would leave that plate and be attracted to that plate, so it'd be a little bit curved right at the ends. A little bit of curvature to the electric field lines. They're not real lines, they're just lines that we draw on paper to help us describe the electric field of that object. You look in the book, they draw electric fields for lots of other things. Like would a positively charged object, it would repel a positive charge, so it would look like that. Just every direction would have equal distant lines. Now, as you move farther away from that charge, that force would become weaker. Not true of the parallel plates. If you move farther from this plate, you just get closer to that plate, so the force remains constant, and hence the parallel lines. So distance between the lines indicates strength, and you can see farther away it gets weaker. Number 12. Define the electric potential difference. Electric potential difference, they kind of leave out the word energy, potential energy difference. But the electric potential energy difference would be how much work each charge could do. Work, let's say it that way, work per unit charge. Math says it a lot more succinctly with symbols. Work per unit charge. It's called electric potential difference. Not only would that charge do work, but it would take work to make it go back where it came from. It can do both. As we'll look at another problem here, that's what batteries do. Somebody did some work on those charges to put them in the battery, and when you turn the key on in your car, for example, those charges go do a whole bunch of work to make your engine turn over. We call that potential difference, or electric potential energy difference, if you want to call it that. 12. I'll just erase real quick instead of poly. Define, oh, that was 12, sorry. Give the equation for electric potential difference. Equation. Well, the symbol we use for electric potential difference is V. It stands for volts, as you could probably guess, and it would be how much work per unit charge. W over Q. The equation for electric potential difference. Give the unit definition of a volt. Well, 1 volt would be 1 unit of work, and the unit of work is, yes, joule. 1 joule of work or energy, it's the same unit for work and energy, per the unit 1 unit of charge. And the unit of charge we had earlier, Coulomb. So it's a joule per Coulomb. So 1 volt means that that charge of 1 Coulomb, it can do 1 joule of work for you. Again, a way of quantifying things that we talk about all the time. We talk about volts, 110 volts in your house, 220 volts for your dryer, 1.5 volt for a AA cell, 9 volt batteries, run lots of different things. Your cell phone battery, not sure, 6 volts. I haven't really opened up one. Your calculator, I know, uses 4 AA's. My remote control for my TV uses 4 AAA's, and they add together to make voltage. Let's talk about that down toward the bottom of the assignment. Next question, 15. What does a capacitor do? Before we get into batteries, a capacitor, maybe you've never heard of a capacitor, but that plastic mayonnaise jar that I had at school with the aluminum foil inside and outside, some guy named Leiden figured out that if you're holding on to the outside of that thing and there's a connection to the inside of that thing, that you holding on to the outside or running it to the ground, we could draw it that way. What if I put negative charge inside? It's got negative charge all over the place. What would that do to the negative charge in the outside? Now you have to keep these separated by a dielectric, which means insulator, right? That's all there is to a capacitor. Conductor, insulator or dielectric, they sometimes call it, and another conductor. It will hold a lot more charge than just one object. The reason? Induction. The inside is negative. Won't that induce the outside to be positive? Induction always causes the opposite charge. But we're not going to let them attract each other because we're going to keep them separated by that insulator. It can still exert force, even through an insulator. Even though the charge can't get through, the force can. So what happens to the negative charge here? Well, it runs into the ground, right? If you run all that negative charge into the ground, well, now the outside is positively charged, right? By induction. Well, that's gonna attract even more negative charge. Do you see how it holds more charge now? Well, the more negative charge comes in, the more positive the outside becomes, which attracts more negative, which repels the negatives and attracts more positive. So we just keep getting more and more positive outside, more and more negative inside. It holds a lot of charge. Depends on some factors, which is the next question, really. What does a capacitor do? Okay, let's simplify the answer. It holds charge. It holds charge by induction. But what does that charge have that we really want? It takes a capacitor to start your car. It takes a capacitor to start electric motors in your home. The capacitors is one of the most commonly used electronic components in your cell phones and computers, so forth. Capacitors are sometimes used to regulate frequencies, but they are also used to store memory and so forth. But what does that charge have? It has energy. That's what a capacitor holds. Why are we interested in charge? Why is charge such a useful thing? It exerts force. It can do work. Yeah, that's why God invented it, to do work for us and hold energy. So there's your answer. Holds charge. It holds energy. Number 16. What is a specific common use of a capacitor? Oh, I just gave a bunch of them. Common uses for capacitors. Start your car. Computers. Cell phones. Volume control on. No, that's a resistor, sorry. If you tune in a radio station, a radio tuner, electric motors in your home. Yeah, just to name a few. There's a it takes a capacitor to start your car, also to start your lawnmower. There's a little capacitor, or a condenser, sometimes people call it, that when you pull that rope, it stores up charge so that you get a bigger spark across the spark plug. Yeah, it's a way of storing. Now, this is not to be confused with a battery or an electrochemical cell. This, you can charge it instantly and discharge it instantly. It's fast. The problem is it doesn't last very long. So it's meant for momentary use. Number 17. So, how do each of these affect the capacitance? Well, what if you just had more surface area? What do you think that would do to the ability to hold charge? here's a general diagram for a capacitor. Let's say that we're going to run this to the ground, and we're going to charge this plate up here, negative. That would run the negatives here into the ground, right? That would make this positive. So what if these plates were bigger? It would hold more charge. Yes, increase capacitance. CAP for short. Increase. How about less distance between the plates? What if you put these closer together? Would they hold more or less charge? Well, they would exert more force. If you were closer together, they're going to exert force. As a matter of fact, by the inverse of the square of the change in distance. So if you cut that distance in half, you'd be 4 times as much force you could exert, and hold more charge. As long as the charge can't jump across, you have to have really strong dielectric between them. But yeah, that should increase. Some of you have made use of those kinds of capacitors. A microphone that's called a condenser microphone. It has to actually be plugged in. It has to have phantom power, some people call it. When you speak into the microphone, one of the plates is very flexible, and it'll move closer to the other plate. Well, when those plates get closer together, it holds more charge, so charge flows on. But then, as you know, sound is a back and forth motion. So as the plate moves farther away, it decreases the capacitance and charge flows off. Closer, charge on. Further, charge off. Charge on, charge off, charge. It's a frequency, and it will exactly match the frequency of the sound that's making it wiggle. Yeah, what a clever idea. And then, of course, all you have to do is take those little flow of charge, which we, in chapter 20, we'll start calling that current. That flow of current that goes on and off of this capacitor can be amplified, sent to a speaker, and makes lots of sound. So a little bit of sound can be turned into lots of sound. Oh, if you've ever driven up to a traffic light where there's a cutout in the actual pavement, you're actually squishing 2 capacitor plates closer together. And of course, it holds more charge. Charge flowing on triggers the traffic light, and it lets it know that you're there. I used to have one of those and opened a gate at the EPA where I worked, and my motorcycle wasn't heavy enough to squish the capacitor plates together, so I had to make a loop around the parking lot and then put on my brakes really hard right on top of that plate to get it to notice that I was there. My bike was not a very big bike. It was a little 200cc Honda Twin Star. Anyway, yeah, but it's heavier than my bicycle. I'd really have trouble running one of these, which, by the way, when I get to a traffic light where I know that has one of these capacitor triggers, I have to use the pedestrian crosswalk and punch the button because it won't see me, so to speak. The optical ones can see me, but the ones that are driven by a capacitor won't. Anyway, that's just some clever ways of making use of capacitors. And the last one there is the question about the dielectric. Polar dielectric. What if you put a molecule in here like water? It has a positive and a negative end. The negative end of the water molecule would line up close to that plate. The positive end would line up close to that plate. And if you put a whole bunch of things like that in here, you are going to essentially increase the force because you've got little force transmitters all through there. And increase force, you'll increase capacitance. So all 3 of those are increase, increase, increase. Number 18, what's the purpose of lightning rods on an airplane? We talked about this in 18A section review, but just real quickly. The pointy end of the lightning rod It's not to attract lightning and run it into the ground. You can't do that on an airplane. It's because charge concentrates at the point. So it dissipates charge. The charge all crowds together on the point and they push each other off. That's like imagining a bunch of kids horsing around on I don't know, a hilltop kind of a point, and playing King of the Hill, and they'll push each other off because it gets too crowded. Charge crowds each other, it repels, and it'll dissipate. Here, I'll say dissipates charge. Dissipates charge. Dissipates charge. And number 19. What if you put 4 1.5 volt cells in series? Let me clean this off. We're about done. All right, wake up there in the back row. We're almost done. Number 19. In series, well, a electrochemical cell, if it's 1.5 volts, by the way, 1.5 volts, that could be a D cell, a C cell, a AA cell, a AAA cell. AAA is for the remote in your TV. They are in series. In your calculators, AA's, perhaps. Now they're AAA's also. But I've seen toys with 4 AA's. Anyway, it doesn't matter whether they're AA's, AAA's, C's or D's. They all have the same voltage. That means every coulomb of charge can do 1.5 joules of work. 1.5 joules per coulomb. Well, then what's the difference between a little electrochemical cell and a big electrochemical cell? The big ones have more coulombs. They can do more total work, but the voltage simply tells you how much work each coulomb does. What if we stacked them? What if we had another one down below and every coulomb here gets energized by 1.5 volts, and every coulomb of the battery underneath it goes. And by the way, they don't have to be stacked like this. But 1.5 volts. So every coulomb of charge that goes from here through some resistor and ends up coming back down to here. Yeah, just what you would think. 6 volts. 6 volts when they're in series. Yeah, this is called series. One after the other. And by the way, one of these does not make a battery. We call it a battery. A battery is actually a series of electrochemical cells, like a battery of tests called the ASVAB, Armed Services Vocational Aptitude Battery. That's a series of tests. So a battery is a series of things. It is, in this case, it's a series of electrochemical cells. But one of them, one electrochemical cell does not a battery make, as Yoda would say. But 4 of them after each other would make 6 volts. So what do you have? 4 little AAA batteries in your remote? That would be a 6-volt battery. Now they may not be stacked in there on top of each other like that. Typically you'll have 2 of them stacked in there like this, and then the bottom of this one, or the top of that one I guess, will be connected to the bottom of the next one. So it'll be internally, you'll put 2 of them in upside down from the other 2. And you still, from here to there, it goes through your remote control. That's just squiggly line, just means anything. Resistance. That would be a 6-volt battery. in your remote control. So whether you stack them all on top of each other or stack two and then reverse the position of the other two and connect the bottoms, but they're still connected in that way. 6-volt battery. Oh, I've got a 6-volt lantern battery. It's a great big thing. Big as your hand. They used to put them in flashlights, big giant lantern flashlights. But if you open one of those up, they have 4 D cells in them. Oh, they still use them for traffic signs, the flashing lights. If you they actually use a 6-volt battery, the big one like that, because it lasts a lot longer than 4 AA's or 4 AAA's. But 4 D cells is still 6 volts, and that's all that's in those great big cans. I have one at school I can show you. But anyway, those are 6-volt battery. Oh, how many would it take to make a 9-volt battery? By the way, a 9-volt battery is actually a battery. And I got one at school. Cut it open, and you'll see 6 little bitty batteries, little cells in there. It makes one battery, 6 cells, 6 times 1.5, 9 volts. So there is actually 6 little tiny batteries, I should say electrochemical cells, inside of a 9-volt battery. So 9 volt is actually a true battery. What if they were in parallel? Number 20. They would look like this. They get bigger as they go. But there's still a coulomb of charge. Connect all the tops. Connect all the bottoms. This would be like jump starting your car. You always connect the positive to the positives and the negative to the negative. Well, if you ran that current through every coulomb of charge would do 1.5 joules of work. Ooh, can't read that. 1.5 volts. Every coulomb, 1.5 joules of work per coulomb. What's the advantage of, well, if you take any of those out, it would still work. Yeah, they're just in there so that the device would last longer. It's a battery of 1.5 volt cells in parallel. Makes it last longer. Yes. Amazing stuff. Again, for us to figure out how to use this force that God's created, this energy that He has created, so that we can get it to do work for us. Man, we use electrochemical cells in everything. And what we don't use electrochemical cells in, we plug it into the wall in a home, which also does work by this force. Let's thank God for it. God, thank you for this amazing force and the way that we get it to do work for us. And the glorious way that you have presented yourself in this orderly, fantastic, beyond our imagination. We love you for taking care of us. In Jesus' name we pray. Amen.